Welcome back to the Natural Hogarithm. Today we're going to be doing another hard daily integral problem. This one's from December 30th, 2025, and it is the integral from 0 to 1 of inverse hyperbolic secant of 2x plus 2 over x squared plus 2x plus 2 with respect to x. Now, before I do begin the problem, I want to really appreciate all of the comments I got last video telling me that I was doing a good job with my explanation, that it was thorough enough. That's really reassuring for me because my goal with this channel is to make things feel as natural and as intuitive as possible, and so the fact that that is getting through to you guys is really valuable to me. But overall, I really want to appreciate the performance in the last video as well. It way outdid my expectations, and I hope I can keep that momentum going with this video and with future videos on the channel as well. So, big thank you to you guys. But without further ado, let's get into the problem. So, today's problem features an inverse hyperbolic trig function, this arc hyperbolic secant, and I think that hyperbolic trig functions in general are a lot less known than normal trig functions, and so I want to begin today's video by previewing what they are, where they find their applications, and also how we do come to define them in a formula, just so that they feel a bit more natural and not out of the blue when I do go ahead and start to solve. So without further ado, let's get into that. Now I want to start by talking about the unit circle, which is something that is probably near and dear to most of us who love math, but for those of you who aren't familiar, it is a circle with radius 1 that we use to define our normal trig function. So if we have a point x comma y that lies on the circumference of a circle, we can define it to have coordinates x equals cosine theta and y equals sine theta. And theta is the parameter that these trig functions, as they're come to define, take in. So theta is an angle, and it defines how far along the arc we've rotated to get to that point. So if we do have cosine of theta, it's really saying, okay, if we've rotated this far, what x value do we expect? Well, we expect an x value of cosine of theta. And for the same reason, if we've rotated an angle of theta around the circle, what y value should we expect? Well, we should expect sine of theta. They're just ways that we define the horizontal and vertical components of a point that lies on a circle. Now, the same procedure is true for a unit hyperbola, only it's a bit different in what parameter we use. So here is our unit hyperbola, highlighted in blue, and then I also have lines going from the origin to a point on the outside of or that lies on the hyperbola, and the way that we define this point is somewhat similar but also has some nuance that separates it from the unit circle definition, and this is where we get our hyperbolic trig functions from. So for a point that lies on the unit hyperbola, its coordinates can be defined by x equals hyperbolic cosine of a and y equals hyperbolic sine of a. Now you'll notice that the parameter here is a and not theta, and that's because we're not actually relying on an angle this time, but instead an area. So we take in an area of a being the yellow shaded region here. We have half the area above and half the area below the x-axis, and we're saying that for a given area, if we've swept out this much area, what point swept out that area? And that would be this point that we drew, x comma y. If we did have this point on the unit hyperbola, well, we could also draw with this light gray line down to its complementary point on the lower branch, and then draw those points, or connect those points back to the origin, and sweep out this yellow shaded area that I've drawn here. And we're pretty much saying, if we've swept out an area of A, what point did this? Well, it would be this point here, x comma y. So that's sort of how we define points on the unit hyperbola, is through area that they've swept out, and not angles, not an arc that they've swept out, like we do on the unit circle. Now, a quick little aside here for why we can't rely on angles to define. I'm going to continue our hyperbola out and draw in an angle of theta here. It's sort of like an angle of inclination up to the point that I've drawn, x comma y, but I'm going to draw a new point now, a little bit further out, and connect this point to that point with a line. That line is not perfect, but the idea is still there. If we do track this line and we say, okay, well, what angle gets us up to our new point, which we can call x naught comma y naught, well, you can see just by the diagram that the angle is pretty similar. And because the hyperbola sort of looks like a line the farther out you go, on the top and on the bottom, this angle isn't going to change much, and so as we go to define points that are further and further out, as x even approaches infinity, the angle is not going to change much, and so we're not gaining too much geometric information from that at all. So an angle is not a useful tool to define points on the hyperbola. We're not gaining as much geometric information as if we went off of areas, because areas add and can be used to distinguish each and every point on this hyperbola effectively. So that's sort of why we use area instead of angles, and that's the key nuance with hyperbolic trig functions, is that we're not using angles, we're using area. Now I'm going to move down to this section because these are actually our hyperbolic trig functions. This is how we go ahead and define our hyperbolic trig functions. So number one is hyperbolic cosine, and we can see that it's equal to e to the a plus e to the negative a all over 2. Hyperbolic sine is very similar, although instead of e to the a plus e to the negative a, it's e to the a minus e to the negative a. And then the third rule, which we're going to be using for this specific problem, and also looks like the normal trig function rule, it's actually identical, is that hyperbolic secant is defined to be 1 over hyperbolic cosine. So the same rule that secant is 1 over cosine. So those are our 3 big rules that we're going to be using today. Not as much 2, but more so 1 and number 3. And that is how we are going to define and work with hyperbolic trig functions in this problem. Now, since our integral also features inverse hyperbolic trig functions, I want to go over inverse trig functions in general, just so it makes sense what we're actually talking about when we are dealing with those features. So, in our unit circle, when we do say cosine of an angle equals x, we're saying if we've traveled this angle, what x value corresponds to that. But how do we isolate the angle itself? Well, if we want to isolate the angle itself to find what that angle is in terms of the point on the circle, that's where we bring in inverse trig functions. So if we have cosine of theta equals x, well, we can apply the inverse of cosine to both sides to get, I'll do this in green, that theta is equal to the inverse cosine of x, or the arc cosine of x. And similarly, for our unit hyperbola, if we say hyperbolic cosine of some area is equal to some x value of our point, well then what is the area? Well, if we apply the inverse hyperbolic cosine to both sides of this, we'll get that the area is equal to the inverse hyperbolic cosine of x, of the x value of our point. And so that's sort of how we go ahead and define inverse trig functions and inverse hyperbolic trig functions. What's really important to take away from this is that an area is defined to be an inverse hyperbolic trig function. So when we do go to work with inverse arcsecant, hyperbolic secant, we are defining an area, and that's going to be very important for how I approach this problem and actually flesh out a solution. So that's all of the information that you need to know, and I hope that that little preview of hyperbolic trig functions maybe makes them feel a bit more natural, or at least not like they're coming out of nowhere. They have a lot of applications that I'm not going to go into in this video, nor am I going to derive where the formulas for hyperbolic cosine or hyperbolic sine come from, because that has a lot of nuance that I don't think really suits a shorter form video about a single integral. But if you are interested, go look them up. There's a lot of information on hyperbolic trig, and I think that there's so much to learn about it, so definitely give them a look. But without further ado, let's get into the actual meat of the problem and determine how we're going to attack it. I rewrote the integral on the next page, as well as the 2 properties we're going to be going off of for the rest of this problem. And the first thing that I noticed when trying to solve this problem was that I don't really know what to do with inverse hyperbolic secant. It's a very confusing function, and what do you really do with integrating it? So my first goal was to rewrite inverse hyperbolic secant in terms of something else, as a different function altogether, so I could re-represent it and maybe have a better chance at integrating whatever I come up with. So that was my first goal. Now let's go through how I actually did that. So I wanted to first work with the general case. We do have this argument here of 2x plus 2 over x squared plus 2x plus 2, and that is quite nasty. I do not want to work with that right now, and so what I'm instead going to do is just kind of come up with a general form for inverse hyperbolic secant of x, and then I can plug in 2x plus 2 over x squared plus 2x plus 2 when I do come up with that new form, that new function that defines inverse hyperbolic secant. So I'm going to start with that general form down here. And remember from the previous page, we went over how inverse hyperbolic trig functions define an area, just like inverse trig functions define an angle. You have cosine theta equals x, so that theta, that angle, is equal to the inverse cosine of x. And the same is true for hyperbolas, only with area, because we're not dealing with angles, but area. So this inverse hyperbolic secant is an area that I'm going to call A. Now I'm going to apply hyperbolic secant to both sides. So I'm going to get that hyperbolic secant of inverse hyperbolic secant, they're going to undo each other. It's just going to be x. And x equals hyperbolic secant of A. Now we also went over, right above as well, that hyperbolic secant of A is just 1 over hyperbolic cosine of A, so I'm going to rewrite that here. I can isolate hyperbolic cosine of A. And now I'm left with that expression. And that's a lot nicer to work with. Remember, I want to find a new expression for inverse hyperbolic secant, but that means that I need to find a new expression for A, right? These two things are equivalent. So if I can find a new expression for A, then I'll be able to work with that and try to integrate that instead. And hopefully that'll be a more usable form that will fit the integral nicely. Now, what we do have over here is that hyperbolic cosine of A equals 1 over x. Now I'm going to zoom out a bit and go back up here. And if we recall, hyperbolic cosine of A is e to the A plus e to the negative A over 2. So I'm going to rewrite that down here in the middle. I'm going to substitute this definition in for this. So there we go. That is our new form. And what I'm going to do now is multiply 2 over to the other side. And now that's what we're left with. Again, what we want to do is solve for A. And if we can solve for A, then we can find a new expression for inverse hyperbolic secant, and then try to integrate that, and we should be good to go. So what I'm going to do now is multiply the entire thing through by e to the A. And that's because this e to the negative A here, I can rewrite it as 1 over e to the A. And so if I multiply that by e to the A, that'll just turn into 1. And it should be a lot nicer to work with if I can go into that form. So I'm going to multiply through by e to the A. E to the A times e to the A is e to the 2A. Again, this just becomes 1. And this becomes 2 over x e to the A. And I'm going to subtract this term to the other side. Oops. That term to the other side. So I'm going to be left with e to the 2A minus 2 over x e to the A plus 1 is equal to 0. Right there. Now, why did I do that? Well, some of you might have already noticed, but this is actually a quadratic. That is a quadratic in terms of e to the A. Right? We have an e to the A squared, an e to the A, and then a constant. That just fits our normal basic quadratic form, ax squared plus bx plus c, only now the variable is e to the A, and this 2 over x just happens to be a constant. So if we want to solve for e to the A, we can just use the quadratic formula, right? So I'm going to bring this over here. Remember, for a normal quadratic, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So that's what I'm going to be fitting onto our problem here. That means that e to the A is equal to, well, negative b, that just happens to be 2 over x, plus or minus the square root of b squared is negative 2 over x squared, which happens to be 4 over x squared, and then minus 4 times a, which is 1, times c, which is 1, so it's just minus 4, all over 2a, which just happens to be 2. And that is pretty much it. Now we know what e to the A is equal to. But before we do take the natural log of both sides to isolate A, I'm going to do some simplifying. Now, one thing I notice is that there is a common factor 4 underneath the square root. I'm going to pull that out first. So this becomes square root of 4 times square root of 1 over x squared minus 1. The square root of 4 is 2. And now the 2 cancels on the top and the bottom. So this 2 cancels, this 2 cancels, and this 2 cancels. And so that is the expression that we're left with. Perfect. Now, one last thing to do before we take our natural log is consider the case of plus and minus, right? We have a plus and a minus case. Now, how do we know which one to pick? Well, if we think back to the geometry of our hyperbola, the area has to always be positive, right? The area itself has to be greater than 0. Greater than or equal to 0. So I'll write that here. Well, if the area is greater than or equal to 0, e to the a has to be greater than or equal to e to the 0. E to the 0 is 1, so e to the a has to be greater than or equal to 1. So that means that this whole thing here has to be greater than or equal to 1. And that's going to be very important in defining which one is actually the right case. Now, we remember from our original integral, which I'm going to go back up to here, our bounds are from 0 to 1, so x is ranging from 0 to 1. Well, what does that mean in terms of our problem down here? Well, it means that for all x from 0 to 1, this term has to be greater than or equal to 1, right? Because this is also greater than or equal to 1. So let's just plug in some value for x between 0 and 1 and see if that's true. Now, I'm first going to try the plus case, and let's check both of these to see. Now we need to choose a value for x between 0 and 1, so I'm going to pick 1/2. Now for our plus case, 1 over 1/2 is going to be 2 plus the square root of, and then 1 over 1/2 squared, which is 1 over 1/4, is just going to become 4 minus 1, which equals 2 plus root 3. And that is greater than or equal to 1. So our plus case does work. Now what about the minus case? Well, for the minus case, it's still going to be 2 minus the square root of 3. And the square root of 3 is greater than 1. The square root of 2 is greater than 1, so the square root of 3 has to be greater than 1 as well. And if the square root of 3 is greater than 1, if we're taking something more than 1 off of 2, well, that's less than 1 now. If something's less than 1, that does not fit our domain, and so the minus case is invalid, so we must take the plus case. I drew something right there. The plus case. That is the correct case. So there you go. All of that little checking there just to determine a plus or a minus. But there we have it. That is our expression for e to the a. And now if we take the natural log of both sides, we get that a is equal to the natural log of 1 over x plus the square root of 1 over x squared minus 1. So this is the expression that we get for inverse hyperbolic secant. This is what we're going to try to integrate for the rest of the problem because it is much easier than inverse hyperbolic secant and will lead to a nicer result. So I've rewritten our integral and also put down the expression that we found to be equivalent to inverse hyperbolic secant of x. Now I'm going to apply this to our integral so that we can have a natural log underneath the integral and try and do some algebra to get it down to something a lot cleaner. So if we rewrite the integral down here, it'll still be from 0 to 1, but now it will be the natural log, and we can't just plug in x, because remember, we're not trying to find arcsecant of x, we're trying to find arcsecant of 2x plus 2 over x squared plus 2x plus 2. So that's what we have to plug in to this natural log. And after all things are said and done, we have this absolute monster of an argument for the natural log, but we are, after all of this, simply integrating a natural log, which is much nicer than what we were originally integrating. And now it is our job to try and simplify this, and make us a clever substitution as well to make our lives a lot easier. So I'm first going to rearrange some of these terms in here. Now we have 1 over the quantity 2x plus 2 over x squared plus 2x plus 2. Since we have 1 over it, I can instead make it the reciprocal. So I'm going to rewrite this as x squared plus 2x plus 2 over 2x plus 2. I've just flipped the fraction. And then I can actually do the exact same thing under this square root, because this square here can apply to the entire term. So I can just flip what's inside, and the square will still be applied. That actually rhymed. So I can rewrite it the same way I wrote the term out there. And now that is our new argument for the natural log. It's not much nicer, but it definitely is nicer. And there's one more algebraic trick that we can apply here to get it to come down to something a lot nicer. And we're also going to do a substitution just to make our lives all the more easier. I'm going to rewrite this term down here so we can work with it a bit more. X squared plus 2x plus 2 over 2x plus 2. And one of the things I noticed when I was looking at this term was that if I do factor out a 1/2, bringing that 2 out from the bottom, we get an x plus 1 on the bottom. And that might seem a bit weird. Why would you do that? What's the motivation behind that? Well, it's because I also realized that x plus 1 squared is equal to x squared plus 2x plus 1. That's almost our numerator. If we add 1 to both sides, then we get our numerator. So this numerator can actually be rewritten as x plus 1 squared plus 1. And that's our new term. We can use that and plug that back in and get a new, nicer form underneath that natural log. So I'm going to go back and plug that in real quick, and then we can do one more step before this thing is looking pretty nice and we can whittle it down to something even nicer. So there's our new natural log term. I've just put the term that we just came up with back into our natural log. And it might not look cleaner at first, but this is now the step where we get everything in terms of a new variable that actually makes things still a lot nicer. So I'm going to do a small substitution here, letting u equal x plus 1. Now, du is just equal to dx, so we don't need to worry about complicating this with any derivatives. It's just a linear substitution. We can go straight in and just translate everything over to u's, but we do need to be careful and change our bounds. So instead of going from 0 to 1, we're going to go from 0 plus 1, which is 1, to 1 plus 1, which is 2. So those are our new bounds. The integral is now from 1 to 2, but it will be a lot cleaner. I'm going to rewrite it down here. So this is our new integral at the bottom in terms of u. I can put a little star next to it, just so we know it's, all special. That's our new integral down there, and it's already looking a lot nicer than what we had, especially from this x plus 1 form, because we're literally just condensing those terms into some single term, which is going to be a lot nicer to work with. But now our job is just to take that argument, take this thing inside of the natural log, and try to do some algebra on it to see if it comes out to something nicer, something that helps us integrate even more, and bit of a spoiler, it does. So let's get into that, which is the second to last phase of this problem. Alright, so I've rewritten the integral on the next page, but we actually don't need much of the integral. What we're going to be worrying about now is this argument here. So I'm going to rewrite it below, and then we're going to try and simplify it to get it down to something even nicer. So I've rewritten the argument down below, and I'm going to go work term by term to try to get this thing simplified. So let's first begin with the first term. Now, this first term, all I'm going to do is simply divide it out. So we have u squared over u, which is just u, and then plus 1 over u. And that's all I've done to the first term here, is expand it out a bit, and it's going to look like that. Nothing crazy. Now, for the square root term, I'm going to expand what's inside. So the 1/2 squared becomes a 1/4. And when we square this numerator here, u squared plus 1 squared, that becomes u to the 4th plus 2u squared plus 1. And the denominator just becomes u squared. I actually need to make this root a little bit taller to fit everything in. And then we still have a minus 1. Perfect. So that is what the argument is looking like after we do that. Now I'm actually going to bring this 4 from the 1/4 back into the denominator, and we will see why in just a second. When I do have my root here, I'm going to take this 1 and make it into a common denominator with the other term. So the 1 just becomes a 4u squared over 4u squared. Of course, this is equal to 1. And when we do go ahead and combine like terms now, the minus 4u squared from this term over here combines with the positive 2u squared over here. 2u squared minus 4u squared is negative 2u squared, all over 4u squared. So that is our now newly simplified term. And what I'm going to do now is bring this 1/4 back out front and get it outside of the square root now. So we do have the 1/4 out front, and the square root of 1/4 is just a half. So I can actually bring out the 1/2 to the front. And that is the new term that we are left with. Alright, so I'm going to rewrite this term down here now, and we're going to do a bit more simplifying. And then I'm going to divide everything out that's underneath this square root. So u to the 4th over u squared, that's just u squared. Negative 2u squared over u squared, it's just negative 2. And then plus 1 over u squared. This final term, doesn't simplify any further. Now one thing I noticed with this term underneath the square root was that it's actually a perfect square. This u squared is just u squared, and the 1 over u squared is just 1 over u squared. But then if we multiply u and 1 over u, we just get 1. And when we do square something, we get 2 times the product of a and b if we square a plus b or a minus b or whatever. And we have a 2 in here. So I was thinking, okay, maybe there is a square that actually equals this. And sure enough, u minus 1 over u squared is equal to u squared, and then it's going to be plus u times negative 1 over u, which is minus 1, and then we do that again, and then we add 1 over u squared. And when we simplify this down, there you have it. U squared minus 2 plus 1 over u squared. So this entire thing underneath the square root is actually equal to u minus 1 over u squared. Now if we have the square root of a square, obviously that's just going to get us what's inside. Oops. And so we're left with this term here. And now that is a lot nicer of something to deal with. And I'm actually going to erase this now, and we can do one final line of algebraic manipulation to get a final answer. So I'm going to expand all of these terms in here. 1/2 u plus 1/2 of 1 over u plus 1/2 u plus 1/2 of negative 1 over u. Well, I can bring the negative out front. And notice that these two terms cancel each other out. And so we're simply left with 1/2 u plus 1/2 u, which is just equal to u. So there you go. The entire argument of our natural log is actually just equal to u. And so this whole big thing, if I zoom out, all of the simplifying we've been doing just proves that the argument of the natural log in our integral is just equal to u. So we can rewrite our integral as such and solve it from there. We're almost done. So if I rewrite our integral down here, it's going to be the integral from 1 to 2 of the natural log of u with respect to u. And that's it. That is what we now have to integrate. So that whole big inverse hyperbolic secant has reduced down to this simple form here, and we're almost done. Now, I went over integration by parts in our previous video, but I am also going to use that strategy here to integrate the natural log of u. The formula for integration by parts is that if you are integrating a function u times the derivative of another function v, this is equal to the product of u and of v minus the integral of the function v times the derivative of u. And that's it. That is the integration by parts formula. Now, Where it gets tricky is picking what u needs to be and what v needs to be, but we actually do have a pretty logical way of going about what to do here. If we do pick something as dv, well, to answer or to re-represent this entire integral here, we need to integrate v. So v needs to be something that we know how to integrate, right? And likewise, whatever u is needs to be differentiated. Well, we shouldn't pick the natural log of u, du, to be our dv, right? Because the entire problem is integrating the natural log of u. We're just reintroducing the same problem again. That's circular, it's not really logical, and it's not going to help us either. So instead, I'm going to let the natural log of u be equal to u. Now this u here is just the u in our integration by parts formula. It's not actually equal to u. Now if I take the derivative of u, I'm going to get 1 over u du, just by chain rule. If we want to pick a dv as well, dv is just going to be equal to du, the only part of our integral left. When we do integrate, we get that v is equal to u. Perfect. So that's our integration by parts substitutions now, and I'm going to rewrite our integral using integration by parts. And what's that equal to? Well, it equals u times v minus integral v du. U times v is u times the natural log of u. I'm just pulling from up here now. Minus, and I'm actually going to remove bounds just so we can get what the actual antiderivative is, because I think it's fun to see what it is. Minus the integral of v du, which just happens to be u times 1 over u times du. Well, u times 1 over u is just 1, so we're literally just left with the integral of du, and the integral of du is just u. It's the thing that differentiates into du. Well, that's just u. So we can see that the antiderivative of the natural log is u times the natural log of u minus u. And we could put a plus c on there, but we're actually trying to solve for the integral from 1 to 2. So I'm just going to slap some bounds on this one. And so all I'm saying is I'm going to evaluate this antiderivative from 1 to 2. And we are almost done. Let's plug in the top bound now, which is 2. So we get 2 ln 2 minus 2 minus, and let's plug in the bottom bound, 1 ln 1. So it's just ln 1 minus 1. Well, ln 1 is 0, so this just becomes negative 1. Minus 1 is just plus 1. And the negative 2 plus 1 is just minus 1. And there we have it. Our integral has reduced to 2 ln 2 minus 1, and that is our final answer. Let's go put a box around it. So there we have it. After all of that work, we finally landed on a final answer. Our inverse hyperbolic secant of 2x plus 2 over x squared plus 2x plus 2 from 0 to 1 has just come out to 2 times the natural log of 2 minus 1, which is about equal to 0.39, and that was the correct answer on the Daily Integral website. Again, thank you guys so much for the feedback on the previous video. I really appreciate it, and keep giving me suggestions if you think I should change things or need to update anything. I'm very receptive to feedback, and I want to make this channel as effective as possible for all of you, so yeah, keep relying on that as a resource, but without further ado, that is our answer. Have a nice day, everyone, and keep integrating.